Well, we are on to video 9, which represents the last video of the boot camp. And so let's see what we're going to talk about. In the last video, we were talking about distinguishing between ionic and molecular compounds, and then we've talked in more detail about ionic compounds. So in this video, we're going to talk about molecular compounds, and particularly how to name them. And then at the very end, a topic called molarity, which was related to the conversations that we had earlier about moles and about stoichiometry. So let's go on and talk about molecular compounds. So when we talk about molecular compounds, we're going to talk about a couple different things to start. What's called the law of definite proportions, and then the law of multiple proportions, which may seem a little bit contradictory, but I'll explain to you. While they're not necessarily they're not contradictory. So let's talk about what we're talking about. So the law of definite proportions says that in every sample of a given substance, the ratio is the same for all the elements present. So in other words, if I've got a pure substance, sodium chloride, in any substance of sodium chloride, the ratio of sodium to chlorine is always going to be the same by mass. If I have a pure sample of water, then the ratio of hydrogen to oxygen in that sample of water is always going to be the same. Now, what the law of multiple proportions says, that it's possible for the same two or more elements to combine in more than one way to form a pure substance. Now, this is particularly true of molecular substances. In general, in ionic compounds, two elements can really only combine in one way. So, for example, sodium and chlorine to form sodium chloride will always combine in a 1-to-1 ratio. That's the only way they can do it. Magnesium and chlorine, when they combine to form magnesium chloride, will always form in a ratio of 1 magnesium to 2 chlorines, and that is the only ratio that they can combine in. So, in general, in ionic compounds, if I simply say what ratio does this metal and this nonmetal combine in, it's always going to be a single answer. But when it comes to nonmetals, they can actually combine in a lot of different ways. And so, for example, carbon and oxygen can combine in 2 different ways. They can combine in a 1-to-2 ratio to give you carbon dioxide, or they could combine in a 1-to-1 ratio to give you carbon monoxide. These are 2 separate compounds, and so they're examples of the law of multiple proportions. You could have a 1-to-2 or a 1-to-1. Now, I just want to make clear, each of these compounds obeys the law of definite proportions, which is to say that in a pure sample of carbon dioxide, the ratio of carbon to oxygen is always going to be the same. And in a pure sample of carbon monoxide, the ratio of carbon to oxygen is always going to be the same, just different from this one. Another example is nitrogen and oxygen. Nitrogen and oxygen actually combine to form many, many different compounds. I've just given you 5 examples here. You can see that they form in a 1-to-1 ratio, a 1-to-2 ratio, a 2-to-1 ratio, 2-to-4, 2-to-5, etc. And so, and that's a fairly unique property of molecular substances as opposed to ionic substances. So we want to talk then about molecular recipes and how they differ in a molecular compound from an ionic compound. In general, a chemical formula shows the kind and number of atoms in the smallest representative unit of the substance. And so when we were talking about ionic compounds, as you'll recall, when we write the ionic formula, say for sodium chloride, and put 1 sodium and 1 chlorine atom in that formula, that is simply representing the smallest whole number ratio that they combine in. A molecular formula actually describes the molecule itself that is the basic unit of a molecular substance. And so CH4 means that there is a single unit that contains 1 carbon and 4 hydrogen atoms that is distinct from the next CH4 unit. It's not just a ratio that these elements are combining in. It actually describes a molecule that is the smallest unit of a molecular substance. Same with carbon dioxide, same with water, and I've shown you pictures of a water molecule before and trying to indicate to you that it is a discrete entity. It's not just a ratio of hydrogen to oxygen. And here's an example from nitrogen and oxygen. This is N2O4 is the formula for dinitrogen tetroxide. You notice that you could divide through this formula by 2 and get NO2, but NO2 and N2O4 are not the same compound. There is a molecule that consists of 1 nitrogen and 2 oxygens, and that's one substance. And then there's a molecule that consists of 2 nitrogens and 4 oxygens, and that's another substance. So it's important to understand that with molecular formulas, that it's not just giving you the ratio, it is actually telling you what elements and how many of them are there in a single molecule. And so because you have this property of molecular substances as opposed to ionic substances, that they can combine in a lot of different ratios, that means we have to use a different naming system. You'll remember for ionic substances, you just simply name the cation and you name the anion, and that's that. But that's because, as I was mentioning earlier, sodium and chlorine can only combine in one ratio, and magnesium and chlorine can only combine in a particular ratio. Aluminum and oxygen are always going to combine in one specific ratio. So you don't have to specify how many of each atom are in the formula, because it just falls out of their ionic charges that they have to combine in a certain way. But that's not true of molecular substances, as I was just showing you earlier. And so we need to use these numeric prefixes that are going to tell us how many of each element there are in a compound. And so I'm not going to read through all of these, but they're the sort of typical Greek prefixes that, if you're familiar with Greek words or with Greek numbers, that they represent. These are the Greek words essentially for these first 10 numbers. So how do we name then? How are we going to name a molecular substance? We're going to name the first element using its full element name, and then we're going to use the second, and then we're going to name the second element as if it were an anion, again changing its name to "ide." And so nitrogen oxide, carbon oxide, nitrogen fluoride, etc. But because we also need to define how many of each element are in the particular formula, we're going to use those Greek prefixes that we saw on the previous slide, with one exception, and that is if there is only one of the first element, then we don't use the word mono. And so let's look at some examples of that. So actually the first 5 examples here are all instances in which there is only one of the first element. And therefore, you'll notice we're not saying monophosphorus, monosulfur. If there's only one of the first thing, we never use the term mono. So here's an example. So here's an example of the law of multiple proportions. There are a couple different combinations you can have for phosphorus and chlorine. This upper compound is phosphorus pentachloride because it's got 5 chlorines. The next one is phosphorus trichloride because it's got 3 chlorines. Similarly, there are different combinations of sulfur and fluorine. I'm not giving you more than one of the possibilities here, but this is sulfur hexafluoride because there are 6 fluorines here. There are a couple different possibilities for combining sulfur and oxygen. And so this compound is sulfur trioxide. This is a different substance called sulfur dioxide. And now here's an example of a compound in which we have more than one of the first element. And so we're going to use a Greek prefix then in that case, dinitrogen trioxide. So here are some examples of compounds that you can try naming. And so if you want to turn the video off for just a second and try to write down names for these, then you can turn it back on and look at the answers. Okay, the first one, P4O10, tetraphosphorus decaoxide, because those are the prefixes, the Greek prefixes for 4 and 10. Dioxygen difluoride. Silicon dioxide, again, because there's only one silicon there, we don't use mono. This is water. You could call it dihydrogen monoxide. Don't ever do that. It literally never has that name. Always call it water. That's why we've stuck this in here, just to say, don't call it dihydrogen monoxide. Carbon monoxide, and this is actually an example that we haven't looked at yet, in which there's one of the first element and there is one of the second element. We do not use mono for the first element when there's only one, but we do use mono for the second element when there's only one. So this is called carbon monoxide. Okay, here are some examples of the flip thing. Instead of looking at the formula and coming up with a name, here is taking a name and writing the formula. So carbon tetrachloride, because it just says carbon, that means there's only one of them. Tetrachloride means there are 4 chlorines, and so CCl4. Disulfur monoxide, the first element is sulfur, di means 2, second element is oxygen, mono means 1. S2O. Sulfur hexafluoride, which we saw on an earlier example. Sulfur, 1, because there is no prefix, that means there's only one of them. Hex means, hexa means 6, so SF6. And then diphosphorus pentaoxide, di means 2, penta means 5, so that's P2O5. Okay, here are 5 examples for you to try writing the formulas. You can switch the video off for a moment, write the formulas, and then turn it back on and see how you did. Carbon tetrabromide, no prefix means there's 1. Tetra means 4. CBr4. Exact same analogous thing for silicon tetrachloride, no prefix, 1 silicon. Tetra means 4 chlorines, SiCl4. Iodine monochloride, no prefix here, and so it's just 1 prefix of mono there, so there is 1 there, ICL. Carbon monoxide, we've talked about already, CO. Phosphorus dioxide, no prefix, so it's 1 phosphorus. Di is 2 oxygens, PO2. So there is a worksheet of naming, writing formulas from names and writing names from formulas that'll be in the worksheet formula for video number 9. And so it'll really give you practice with doing both things, writing formulas from names and writing names from formulas. One last thing we want to talk about real quick that's just kind of a little bit of errata, which is to say, these are elements that exist not as single atoms, but as diatomic molecules, and there are 7 of them. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. There are various mnemonic devices to remember these 7. Hofbrinkel kind of sounds interesting. That's one that one of my former students had, Hofbrinkel. Honkel-Briff is another way that I learned it, and so that, again, it's the same 7 things, just arranged in different ways. This is something that Ms. Fogarty came up with. Clowns never have breakfast on icy Fridays. That gives you your 7: chlorine, nitrogen, hydrogen, bromine, oxygen, iodine, fluorine. Or to consider that if you exclude hydrogen and just look at nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, they form a 7 on the periodic table, and there are 7 of them. But you have to throw out hydrogen to do that, so it doesn't work all that well. So I'm for Hofbrinkel myself, or Honkel-Briff. Those are the simplest way to remember these things. All right, now on to something completely different, and that is concentrations of solution. When we talk about the concentration of a solution, and that is when we've dissolved some substance in a say a liquid solute, a solvent, we talk about its concentration in terms of molarity, and molarity is defined as moles of solute per liter of solution. And so we use the capital M, typically italicized, to represent the unit of molarity, which means moles per liter. And so if you know the chemical formula of and as we went back and did in roadmap number 1, if you know the chemical formula of the particular solute and its mass in grams, you can calculate the number of moles. So where does this leave us in terms of doing some calculations? I've got a worksheet for you to do some molarity calculations. It works like this. Molarity is moles of solute per liter of solution. And as I said on the previous slide, M, the italic capital M, represents moles per liter, which is molarity, the unit of the SI unit of concentration. Well, here's a new roadmap, roadmap 3, which allows you again to get on the road at any one of these 3 boxes and get off the road at any other box. So in going from some particular place to another place, you're simply going to follow the arrows and do what it says above the arrow. If you're going from left to right, you're going to do the operations above the arrows. If you're going from right to left, you're going to do whatever operation or operations are listed below the arrows. So let's just try an example of this and see what happens. What is the molarity of a sugar solution made by dissolving 1 gram of sucrose in water to give you a total of 50 milliliters? And as a part of this, you need to know that the molar mass of sucrose is 342.3 grams per mole. Well, if you know that you've got 1 gram of sucrose, you are going to now convert that to moles. And so we do that by dividing by molar mass. So 1 mole of sucrose is 342.3 grams. That eliminates grams, and we've got moles of sucrose. That is in 50 milliliters of solution. But remember that molarity actually is in moles per liter, and so to get milliliters into liters, we've got to do one more operation, which is that 1 milliliter is equal to 10 to the minus 3 liters. And when I do that, I get an answer which is 0.058 moles of sucrose per liter. So that would be the molarity of the solution, 0.058. Let's just quickly back up for a second and look at the roadmap. We were given grams of substance. We were asked for the molarity of the solution. What this tells us to do is to divide by molar mass and then divide by the volume. That is essentially what we did here. We took our 1 gram, we divided by the molar mass, we divided by the volume. We had to also do an additional operation to convert milliliters to liters, and then we got our answer. And we can write that as in scientific notation, which is often a simpler thing to do. All right, let's go the other way. If I've got 1.25 liters of a solution that is 0.10 molar in hydrochloric acid, how many moles of hydrochloric acid or hydrogen chloride are contained in the sample, and how many grams of hydrogen chloride? So this is just a simple dimensional analysis problem. I'm given as a measurement. I've kind of written this backwards, and so if I had a second to stop and do this over, I would probably just reverse these, but you get the same answer. My measurement is I got 1.25 liters of solution. And I know that its molarity is 0.1 mole per liter. That, remember, molarity means moles of solute per liters of solution. And so I take my 1.25 liters of solution, I multiply it by 0.1 mole per liter. That cancels out liters of solution. I'm left with the unit of moles of hydrogen chloride. I do the operation, I get 0.13 moles of hydrogen chloride. If I want to figure out how many grams, I'll just extend that same calculation. Again, I'm starting with 1.25 liters. If I was rewriting this, I would flip this. I would put these two things here, and I would start with the 1.25 on the left. 1.25 liters of solution times 0.1 mole per liter, and then I'm going to multiply by 36.46 grams per mole. That's the molar mass of hydrogen chloride. That gives me 4.6 grams. And so there we go. there are, like I said, there is a practice sheet for this, worksheet for this. There's also a copy of roadmap number 3 that will be in the folder. We've come to the bitter end of the whole boot camp. I hope things are going well for you. Again, please don't hesitate to contact with me with any questions, and we will otherwise see you in August. Bye-bye.